Hey, I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah! Check out my new weapon. Piranha gun! Oh, yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Doing a demonstration. Oh, ah! It's so difficult sometimes to get the blind back inside.
Welcome to the lesson, the video lesson on vectors. I hope you enjoyed that little introduction. As you've already done some reading and note-taking on, vectors are quantities that contain both magnitude and direction. They are opposite of scalars. Scalars contain only magnitude. And as you've already learned as well, examples of vectors include displacement, which is direction with distance, velocity, which is speed with direction, acceleration, force, momentum, anything that's a field, gravitational field, electric field, magnetic field, are all examples of quantities that contain both magnitude and direction. The focus of this video is not to sort that out, but rather to learn how we add multiple vectors, and we're going to just start with two. How do we add vectors together and get what is called a resultant? Not a stretch here that the result of adding two or more vectors is called a resultant. All right, so let's jump in here. We're going to start with two vectors at 0 degrees to each other. We'll explain more about what that means here in a moment. But we'll start with a vector here that has 4 units worth of length, or a magnitude, we'll say. 4 units worth of magnitude, and its direction is to the right. If we have a second vector that is 0 degrees to that vector, if we think of the rectangular coordinate system, or otherwise called the Cartesian plane, think about where 0 degrees is on that, and it's on the positive x-axis. So if we were to say a second vector was at 0 degrees to this vector, that means from the tip of the first to the tail of the second, the measurement would be 0 degrees. So it looks something like that. Let's have this second vector have a magnitude of 3 units. And so we have here two vectors that are 0 degrees to each other, one with a magnitude of 4 and the other one with a magnitude of 3. Well, what would the resultant be? Clearly you see that all we would have to do here is add the two vectors together, since they're pointed in the same direction, and the resultant, which we would label R, is one vector that represents both of them, and that resultant would have a magnitude of 7 units, and its direction, which we would indicate, would be at 0 degrees. Okay? We use the rectangular coordinate system because it's a system that everybody can speak a common language with. That's how we express our answers relative to the rectangular coordinate system. The key thing to take away from here with vectors that are at 0 degrees to each other is that when they are added to each other at 0 degrees to each other, they always will produce a maximum value for the resultant. You can never get a larger value than when adding 2 or more vectors at 0 degrees to each other. All right, let's move on to the opposite case, where we have 2 or more vectors at 180 degrees to each other. So let's start off with that same 4-unit vector pointed to the right. What would it mean to have a second vector at 180 degrees to the first one? Well, that means from the tip of the first to the tail of the second, the angle measurement would be 180 degrees. Where does that lie on the rectangular coordinate system? Of course, it lies on the negative x-axis. So it would look something like that. And then we go ahead and label that same vector that we had up above, but pointed in the opposite direction. Okay. So what would our resultant be? Well, it would go from where we started to where we ended up, and so our resultant R would be, in this case, 1 unit of magnitude at, what's the direction of our final resultant? Well, it lies in the positive x direction. So we would say that its direction is at 0 degrees relative to the rectangular coordinate system. Okay. Again, there's another key point here. That is, when adding 2 or more vectors 180 degrees to each other, you always produce a minimum value for the resultant. You can never get a smaller value than when you add 2 vectors at 180 degrees to each other. What that also means is that it is possible to get any resultant in between the max and min values. If we were to look at these 2 examples in front of you right here, we know that if we were to take and put the 3-unit vector at any angle between 0 degrees and 180 degrees to the 4-unit vector, we will always get a resultant that lies somewhere between 7 units and 1 unit. Okay? All right. What about this question? When does 3 plus 4 equal 5? You might say, well, that can never happen. 3 plus 4 equals 7. Not in vectors. 3 plus 4 could equal 5 if the 3-unit vector and the 4-unit vector were at 90 degrees to each other. Let me illustrate. Let's take that same 4-unit vector and take our second 3-unit vector and put them 90 degrees to each other. The resultant would go from the tail of the first to the tip of the second. Would look something like this. And to determine its magnitude, what's nice about this situation is that you can clearly see we have a right triangle. This, of course, allows us to use trigonometry to get the answer, specifically any of the trig functions and or Pythagorean theorem. So to get the magnitude of R, since R is the hypotenuse, R squared would equal 4 squared plus 3 squared. 4 squared is 16. 3 squared is 9. 16 plus 9 is 25. So to get R, we would take the square root of 25, so the answer would be 5 units. We kind of knew this already before doing that, because when one of the legs is 3 and the other leg of a right triangle is 4, the hypotenuse is 5. It's a 3, 4, 5 triangle. Okay? Remember, though, when writing answers for resultants, we also have to include direction. The symbol we use for angle in physics is theta, T-H-E-T-A, the Greek letter, and it's simply an O with a line through the middle of it. So the Greek letter theta represents our angle that we need to find that. What trig function would allow us to find that angle using the given information and not calculated information? Well, we have a 3-unit vector that is opposite the angle and a 4-unit vector that is adjacent to the angle. That sounds like tangent. So tan of theta would be opposite 3 over adjacent 4. How do we just get the angle? We do that by taking the inverse tangent of 3 over 4. And I believe just to 2 digits, that would be 37 degrees. So to express our final answer here, we would say the resultant is 5 units, whatever the units are, at 37 degrees on the rectangular coordinate system. Okay? So we have 3 examples there of how you would do that. One at 0 degrees, one at 180 degrees, and one at 90 degrees. We'll talk later about what if you have a situation in which it's not one of these 3 scenarios. Okay? Next, what we want to talk about is how do you take a single vector and resolve it into its components. This is the process called vector resolution, resolving a single vector into its components. To start off with here, we're going to let our vector be a force. It's easier to think of it to start off with that way. A force of 15 newtons. So we're going to say F for force equals 15 newtons, which is the unit of force. And our force of 15 newtons is at 30 degrees on the rectangular coordinate system. Okay? Components always lie in either the x-plane or the y-plane. So this force has a component in red here that lies in the x-plane, and it has a component in green here that lies in the y-plane. We want to be able to calculate those 2 components. Okay? Well, you can see that if we extend the green component over to the right, that we would get and form a right triangle. This is the beauty of finding components because, again, we can use trigonometry to find this x component, which we will call fx, and this y component, which we will call fy. All we have to do is use our trig functions to do it. All right, let's give ourselves a little space here. Okay. All right. Let's start with the x component. What trig function relates the hypotenuse of 15 newtons and fx, the adjacent side, to the 30 degrees? The answer, of course, is cosine. The cosine of the angle would be adjacent, fx, over hypotenuse, which is f. So fx equals f cosine theta. We're going to want to remember this because this is going to get used a lot in the course, that the x component, if the angle is measured from the x-axis, we will be using cosine to find that component. Solving this particular question, fx is 15 newtons times the cosine of 30 degrees. Go ahead and calculate that on your calculator. Pause the video if you need to and need time. 15 times the cosine of 30, checking your answer, is 13 newtons. Likewise, moving to calculate the y component, what trig function relates the y component in green, the 15 Newton hypotenuse, and the 30 degrees? That would, of course, be opposite, hypotenuse, sine. So the sine of theta is Fy over F. So Fy is F sine theta, multiplying both sides by F. Again, we're going to want to remember that. Continuing on with this problem, in this particular example, we would have Fy equals 15 newtons times the sine of 30 degrees, which everybody should know is 1/2, and half